Okay, let's get started again. This will be part 2 of our deep learning in AI, what you need to know. And last time we stopped with radiomics. Now, the way you think about radiomics, maybe this in an easy way. When I look at a CT scan, I look at all the information I could see on the scan. I change windows, I zoom up, I look around, I do all sorts of reconstructions. Radiomics really then takes things to a new level. It's looking at things, it's extracting information from images that you really can't see within the images. And a lot's been written about radiomics for detecting lesions, for differentiating lesions, for determining how patients respond to chemotherapy, and many other things. The premise is that imaging data conveys meaningful information about tumor biology, behavior, and pathophysiology, and may reveal information that is not otherwise apparent to current radiologic and clinical interpretation. And so you think about it, and here's just an article by Scheer going through it. You have data, you're looking at the data, and then what you start doing is taking features from the data, looking at all sorts of extractions, model interpretation, and performance evaluation, all sorts of different things we look at. And then we do all sorts of things like looking at shape features. We run different filters on the information. And when you think about it, radiomics is a promising non-invasive tool for the diagnosis and clinical management of pancreatic tumors. It provides a more adequate and reproducible measurement of the tumor than other methods. In addition, the combination of radiomics and genomics has a promising future. So when we talk about radiomics, we're not saying that it's replacing anything. It's an additive. Linda Chu wrote an article about the radiomics features to differentiate pancreatic adenocarcinoma and normal tissue, and patients were classified with a sensitivity 100% and a specificity of 98%, separating tumor versus normal pancreas. This becomes very, very important. And here's just a good example. You have the input, you have a CT scan, and you look at first order and second order statistics, you look at different filters. Sometimes you can have 50,000 different features in radiomics. Obviously, not all of them are going to help, but then you bring it down to somewhere between 10 and 50 features that you look at. We look at random forest classifiers of this information, and then we create what I would best call a fingerprint. We need to think about how the information is unique, how it's different, how normal is different than abnormal, how an adeno-CA looks different than autoimmune pancreatitis or looks different than a serous cystadenoma. And we create these different models, and so when we're shown new cases, we're able to put lesions specifically into unique categories. And as mentioned, this was nearly 100% in distinguishing between pancreatic cancer and a normal pancreas. Again, 40 radiomics features were selected for the random forest classifier, and you could see for yourself amazing accuracy, sensitivity, and specificity. There are a number of other articles. We looked at a wider range of benign and malignant lesions of the pancreas, which were cystic, looking and seeing how good radiomics was compared to an experienced radiologist. And we were able to show that the accuracy of radiomics-based cyst classification was in fact better than a radiologist. And again, you think about that, these are expert radiologists who see lots of pancreatic lesions. Imagine in the community where people don't see as many lesions. I'm not saying people are not as smart. I'm just saying that I've seen, for example, hundreds of serous cystadenomas and MCNs and cystic neuroendocrine tumors and millions of IPMNs. So someone who sees a lot of them is likely going to do better. But even in that audience of people, still the radiomics was in fact better. We also know this is true with neuroendocrine tumors. We've looked, and radiomics is more accurate than radiologists in detecting the presence of a neuroendocrine tumor. The grading of tumors, Whether things are grade 1 or grade 2 and grade 3 become important, because grade 1 you simply can follow. They're usually smaller tumors. And now under 2 cm for neuroendocrine tumors, people will simply follow. And it ends up that radiomics is better than EUS with biopsy and pathology, because often you don't get the right pathology when you sample the tissue. With radiomics, we're looking at the entire process, and so radiomics for neuroendocrine tumors is actually more accurate. When we think about the entire spectrum in the pancreas, detection, classification, and prognostication all become very important. In this article by Wang, CT-based radiomics analysis based on the whole pancreas can distinguish cancer patients from healthy individuals, and it could potentially become an early detection tool for pancreatic cancer. So just think about it. What if every scan you did radiomics? Could that pick up all the early pancreatic cancers? Well, at the Mayo Clinic in the past year, they've done lots of work looking at the pancreatic cancer patients who had scans done for other reasons 1 to 3 or 4 years earlier. And what they found was that radiomics-based models could detect pancreatic cancer years before, when it wasn't visible even in retrospect to the radiologist. And here are 2 important articles that are addressing that. We spoke about that before. We'll speak about that again in more detail. But radiomics can see things 3 years earlier in many cases, where even in retrospect, the radiologist can't find the tumor. So imagine 3 years earlier, those are stage 1 tumors. Those are 80% 5-year survivals. Think about it. In a review of that article, Michael Rosenthal made the point, these features are not discernible in visual assessment and do not meet the threshold for radiologists to report, but are biologically plausible given existing evidence that pancreatic cancer affects broader pancreatic function early in the disease process, and that machine learning-based radiomic analysis may be a novel strategy to screen for pancreatic cancer by revealing changes in the pancreas that precede the development of pancreatic cancer and the emergence of a radiological detectable mass. So this becomes very, very important. This article by Itakura, CT-derived radiomic features predict rapid tumor progression following SBRT. So one of the things I mentioned before, we're looking at pancreatic cancer with radiomics to determine what chemotherapy will work on an individual patient. And here they're looking at what patients will progress. So we can really determine what patients should get chemotherapy and then surgery, and which patients doing surgery is really not going to help those patients. In this article by Kim, American Society of Clinical Oncology made the point that they developed models that compute the probability of the patient having spread based on the routinely collected data from patients with advanced or metastatic pancreatic cancer. To the best of our knowledge, this is the first machine learning solution aimed at aiding clinicians in the selection of the first-line chemotherapy regimen for pancreatic cancer. Again, predicting response. An article by Galuza, Radiomics is science based on the quantitative analysis of medical images by mathematically obtaining a series of values representing signal intensities or a variety of pixel interrelationship metrics. Again, what we're thinking about is being able to analyze the information from the CT scan. Detection of disease, choosing management, predicting follow-up, predicting outcomes are all things that are possible using radiomics. And this today was published. This was our work looking at lymph node metastasis and non-functioning neuroendocrine tumors with the radiomics clinical model, and showed how strong radiomics was in predicting the response in these patients. We also then have spent a lot of effort segmenting out the pancreas. So we taught the computer to recognize the various organs, especially to recognize the pancreas. With manual segmentation and deep learning prediction being about equal, we're able to look at the pancreas carefully and detect the presence of pancreatic cancer. Again, what do? You teach the computer how to recognize the normal pancreas and then how to recognize pancreatic cancer. This becomes a very classic thing. Lots of work being done in this area. Also work being done to recognize the pancreatic duct and the transition point when the pancreatic duct is obstructed. We spoke about that before, but you can see how important it is. And again, thinking about the potential for developing algorithms for detecting pancreatic cancer early. I think also we need to do is train the computer to find the pancreas. In our work, we've been segmenting the pancreas by hand. We do a great job, but it takes up to an hour a patient. What you want to be able to do is have the computer do everything for you. And this article by Dr. Kawamoto speaks about that. And then when it can pick up and isolate the normal pancreas, you then want the computer to find and outline the cancer, and then the computer to do the radiomics, and then at that point the radiologist will look at the images and put everything together. In conclusion, our study found that segmentation of the pancreas using deep neural networks is accurate and can be applied for AI-based volumetric analysis in the majority of cases. So again, AI will become and is becoming a critical part of how we do things. There was a good article in Lancet by Topol and Matre. Cumulatively, what about the majority of patients with no risk factors who present an advanced stage? Talking about detecting pancreatic cancers, not just in high-risk patients where people have done different studies looking at doing EUS and MR and CT, but what about everybody else? What do you do with the pancreatic cysts? Who are high-risk patients? And this article makes the point that we may be able to look at all of these patients by looking at the fact that we can use AI to predict which patients are at a higher risk by looking at the EHR data, looking at the images, looking at liquid biopsies, looking at lots of bits of information. So very exciting. Now, I mentioned we need to segment out the pancreas, and we do it by hand. Well, this work with Microsoft, and it's an article we just submitted, supported by Lustgarten, trains the computer to accurately find the pancreas and define its borders. And we compared the result of the computer program with our best radiologists and our best segmenters, which are some of our technologists, and found that the accuracy was essentially the same. Both made errors, but it looks like the AI in 95% of the cases could be nearly perfect, and in about 5% of the cases, it's going to have some issues. The issues tend to be in patients who have fatty infiltration of the pancreas, patients who have poor abdominal fat planes, or where there's inflammation near the pancreas. But again, if 95% of the time the computer is correct and it tells you when it has a problem, so you could do the 5%, that's going to save a lot of grief. And the article shows how we're getting better. We'd like to take that 5% and decrease it to 0%. Maybe we can do it, maybe we can't, but at 95%, it will change how we do things. Now, it's important to be accurate with automated segmentations or manual segmentations. The whole use of radiomics is based on accurately being able to localize the pancreas. You can't do radiomics if the accuracy of the segmentation is not good, because if you pick up other tissue, it may confuse things. So it's important that you need to build this, and we want to build it into a flow chart where it's little involvement by the radiologist, because if you want to screen all patients coming through, you need to have the computer be doing everything, and only at the end, when it's abnormal, will the radiologist get involved. Now, another thing is, of course, IPMNs. We talk about these cystic lesions and how ACR guidelines is a 9 or 10-year follow-up. 97% of IPMNs do not become malignant. It's less than 3%. The question is, how do you find this 3% without rescanning everybody? You know, basically, 10 years is not even the right answer, or 9 years, because since patients with IPMNs have field defects, it's really a lifetime of potential increased problems. So what is it that we can do? Well, one of the things we can do, of course, is use computers perhaps to be able to pick up these lesions. One of the studies that was done was a multi-center trial where they looked at cystic pancreatic lesions, and all the lesions that were of concern went to surgery. It ended up that only 40% of those lesions, which were felt to be premalignant or malignant, actually had premalignant or malignant features, and 60% of the patients had surgery for no reason. There was then a program developed called CTisus that was more accurate, and in 60% of the cases, not 40%, it was able to accurately triage the patients. So it did better than the physicians themselves by increasing the distinguishing features that allowed you to determine who should or should not go to surgery. And again, CTisus was good, but still 40% of patients went for surgery when they didn't need to. And those are surgeries that are distal pancreatectomies or Whipple's procedure. CTisus had the potential to reduce patient morbidity and economic costs associated with current standard of care pancreatic cyst management, but it still was wrong in 40% of the cases. And so that brings us up to how can we do better? And for that, we worked with Microsoft to better understand how we can do this. Or the question is, could we do this? Can we look at the same data, perhaps, and be able to be more accurate? This article is in press as of a week ago. You can look at it. It's open access so everyone can read it. And we looked at the performance of Explainable AI as developed by Microsoft to guide the management of a patient with a cystic pancreatic lesion. What do we do? You can see the first two authors are Microsoft, Juan and Felipe. The last two senior authors are me and Anne-Marie Lennon from Hopkins, and Anne-Marie is now at Pittsburgh, and a lot of the Hopkins people in between. So let's do this. Let's take a break here since I want to cover this all in one fell swoop. And let's come back and speak about how we used AI for really changing the outcome for patients, because at the end of the day, the Microsoft using Explainable AI reaches the 90% accuracy, not the 60%. And that indeed is very exciting. So let's take a break and come back in a few minutes. If you like this video, make sure to subscribe to the CTisus YouTube channel. You can also visit us at ctisus.com for even more videos, plus quizzes, pearls, protocols, and oh so much more. We're also in the App Store and have well over a dozen apps for iPhone and iPad, all completely free. Thanks for watching.